Hi, I'm Abhish and I'll be presenting our work, a novel 3D UNet deep learning framework based on high-dimensional bilateral grid for edge-consistent single-image depth estimation. Monocular depth estimation has traditionally been an ill-posed problem because of rich geometric details or because of occluding contours in the image. However, it has widespread applications in augmented reality, in virtual reality, not in robotics, and in particular nowadays in autonomous cars. Autonomous cars generally resort to the stereo depth estimation problem. They have multiple cameras to capture multiple views of the same scene. However, with monocular depth estimation, we can actually reduce the hardware and infer a depth map of similar quality. How we model this problem is we use the concept of bilateral grids, which is a unique 3D data structure for an RGB image. And we encode it using a 3D UNet. So our novel architecture is based on the 3D UNet architecture. And we encode it using that architecture and we obtain a sharp geometric layout. This geometric layout has accentuated and prominent edges. We use this sharp geometric layout and we propose another integrated architecture, and we obtain a depth map which is of high quality and which has sharp edges as well. The existing methods today generally use various kinds of losses like the gradient loss and so on, and also uses methods like normal geometry consensus, and they can capture fine details. However, the reason for failure for a lack of sharp edges in depth maps are, first of all, the depth annotations which are available, they might not have sharp edges. And also because there are occluding regions in the image, or there might be minute objects or details around edges which might go missing in the RGB image. Our contribution is twofold. First, we propose a novel architecture based on the UNet architecture called 3D BG UNet. And this architecture, this first part, it actually infers a sharp geometric layout which has accentuated edges. We combine this with an edge map and a segmentation map of the same RGB image, and we infer a depth map of high quality with, again, prominent edges. The concept of bilateral grids is as follows. It's a 3D data structure, so it has 3 dimensions, X, Y, and Z. The X and Y correspond to the spatial position of the pixel. So every RGB image can be converted to a bilateral grid, and every pixel has a position, and this position is represented by X and Y coordinates in the bilateral grid. While the Z axis, it corresponds to the intensity value of that pixel. Now, why do bilateral grids preserve these edges is because edges are just sharp rises or falls in intensity values, right? In pixel intensity values. So because bilateral grids, they have that third dimension to separate pixel values, not only by their spatial position, but also by their intensity values, they are able to preserve edges during processing. The pipeline is very simple for any bilateral grid oriented process. We have a 2D image, we convert it, we lift it to a higher dimensional space. This data structure is called bilateral grid. We do some processing within the grid. We obtain a processed bilateral grid, and then we perform slicing operations to obtain a 2D image. Here is how bilateral grids are constructed. We first initialize all the values in the bilateral grid to 0, 0, and we do some sampling in the spatial axis and in the reference axis, and we increment it by the intensity value, 1. Now the sampling rate, there are 2 sampling rates. First is a spatial sampling rate, which is SRS on the slides, and the other sampling rate is that of the reference or the intensity axis, which is SRR. The SRS basically controls the resolution of the bilateral grid, and the SRR basically controls the degree of edge preservation. And why bilateral grids are so promising is because even though people perform aggressive downsampling on bilateral grids, they are still able to obtain high quality results, and we observe this uh, in our own application. This is the proposed architecture, and it's based on the UNet architecture. Uh, how this works is so first there's a contracting path which downsamples and encodes the bilateral grid, and there's an upsampling path which reprojects it back to the same shape as the input bilateral grid. Each block in the contracting path has two convolutional layers followed by a downsampling layer. Now this downsampling layer is just a max pooling layer. Uh, the upsampling path or the expanding path, in every block, it has two convolutional layers followed by a deconv layer, which performs the upsampling. How this is based on the UNet architecture is we convert all of the convolutional layers to 3D. So 2D convolutional layer becomes 3D, 2D max pooling layer becomes 3D max pooling layer, and so on. The input to this network, the 3D BG UNet, also known as 3D bilateral grid UNet, is the bilateral grid which we obtain from the RGB image using the process I described earlier. And the labels are, we also project the depth maps to the bilateral grid, and we use mean squared loss for this particular architecture. The second, the integrated architecture. So the first architecture, we obtain a sharp geometric layout from the bilateral grid. To further improve and obtain a depth map, we use an integrated architecture which is called 3D BGES UNet, which also stands for 3D Bilateral Grid Edge Segmentation UNet. And how this works is we leverage information from three sources. First, from the sharp geometric layout, which is very crucial for this network, the edge map and the segmentation map. We concatenate these and we obtain a tensor which has 5 channels. For the edge map, we used a network called DexiNet, and for the segmentation map, we use a pre-trained model called lightweight RefineNet. The labels here again are the ground truth depth maps. This architecture is a 2D UNet encoder decoder architecture, and it is not 3D as the earlier architecture was. Here again, we use mean squared error loss to train the model. This is the overview of the 3D BGES UNet architecture, which combines the three sources which I was talking about. It concatenates these three sources, from which are crucial to obtain a sharp edge consistent depth map. These are our qualitative results from the first network, the 3D BG UNet network. And if you can see, the edges are so prominent in all these geometric layout images, especially this picture of the chair. The edges are so prominent in this picture. These are our final results. If you see the third column, you can notice how prominent the edges are. The other images, they tend to be more hazy, but our images have sharp edges because of the bilateral grid. The quantitative results, we perform quantitative comparison with other approaches on 4 metrics: the RMSE, the log10, the MSSIM, and the DERM metrics. And in all cases, our metric values are better than the methods we've compared with Serial UNet, with SharpNet, and with MSDN. Again, these are our RMSE results. And as you can see, our results are way better compared to other methods. We also do a sort of combinational analysis. So we want to assert the importance of the geometric layout which we inferred from the first depth map. So we do various combinations. We do RGB plus segmentation plus edge, RGB plus segmentation, and RGB plus edge, and then Rs, which is the sharp geometric layout plus segmentation plus edge. And it is noticed that our results on all the metrics are far better than all the other combinations. And this asserts the importance of bilateral grids, the geometric layout, which we obtained. These are a few more qualitative results which we wanted to show, especially because how prominent the edges are and how hazy uh, the results are for the other combinations. The third column is ours, and the edges are so prominent, while in others they are blurry. Our first network, which infers a sharp geometric layout, it takes 8 hours to train, and the integrated architecture takes around 11 hours to train. The testing time for the first network is 0.61 seconds, and for the second, it's 0.18 seconds. We have, however, not done batching or parallel processing, and we've just inferred one image at a time. We would like to conclude by saying that we use two networks. The first network is the 3D BG UNet, and the second network is 3D BG ES UNet. And this is based on the high dimensional 3D data structure called Bilateral Grid. And the first one infers a sharp geometric layout, and the second one, the second integrated architecture, it will infer a very high quality and depth map with prominent edges. The major advantage of 3D BG UNet is that it is a versatile model. So we can actually use the inferred geometric layout in various self-supervised methods. For example, there's this architecture which uses SGM for depth hints to predict good quality depth maps. And we can actually provide geometry suggestions using our 3D BG UNet. With future work, we would like to experiment with other loss functions, such as the gradient loss function. And we would also like to delve deeper into monocular video data, or especially in self-driving cars, for example, you have video data, right? You don't have images. And we would like to delve into these aspects of depth estimation as well. Videos will have the temporal dimension as well. So we would like to deal with higher dimensional bilateral grids in this particular video data. And we would also like to apply our network to various applications, real life applications like image manipulation or editing, image to image transfer, or object recognition, or realistic integration with VR/AR. Thank you.